Welcome everyone to today's presentation on stack bonding, presented on behalf of ThinkBrick Australia. So just some background information before we begin. This presentation will discuss relevant standards involved in stack bond design such as AS3700 masonry structures. This presentation will also look into different failure mechanisms as well as detailing requirements as part of stack bond design. Stack bonded masonry is a form of construction in which the masonry units in adjacent courses are aligned vertically above one another. As you can see on the picture on the right, the masonry units can be stack bonded horizontally or vertically. Stack bonded masonry is becoming more prevalent in designs for architectural effect and are used as non-load bearing walls. Australian standard AS3700 masonry structures includes provisions for the design of stack bonded masonry. A masonry wall is classified as a stack bonded wall if the masonry unit overlap in successive courses is less than 1/4 of the unit length or 50 millimeters. The larger value shall be used. Although provisions in AS3700 predict zero horizontal bending strength, stack bonded masonry is becoming increasingly specified in designs incorporating architectural effect. In these cases, specific structural design requirements are required. The University of Newcastle has conducted research on the horizontal bending capacity of stack bonded walls. The schematic elevations shows a simply supported stack bonded wall. A steel angle airbag surrounds the frame, while an airbag is placed in front of the wall to measure displacement. Figures B and C show the horizontal and vertical orientation respectively. Horizontal bending capacity in a stack bonded wall is similar to its vertical bending capacity, where flexural stress act normal to and cause failure along the lines of the perpends rather than along the lines of the bed joints. In the unreinforced stack bonded wall, the bending capacity is limited and governed by the bond strength of perpend joints. Hence, brittle failure occurred along the line of the perpends and resulted in sudden and complete loss of capacity. In the reinforced stack bonded wall, there was a more ductile response and greater deflection was measured. Now we will look at some design principles, which include design requirements, detailing requirements, and finally a worked example on horizontal bending. A stack bonded wall is much weaker in horizontal bending than a running bond wall because the continuous head joints open easily, presenting little resistance to horizontal bending. This is shown in Figure A. In a running bond wall, the masonry units have to overcome the shear resistance at the bed joints before the head joints can open. This is shown in Figure B. Masonry shall be designed as unreinforced for compression, shear, and vertical bending. Our TBA 06 manual outlines design requirements for compression, while our TBA 04 manual outlines design requirements for shear and vertical bending. These manuals can be found in the technical section of our website. Masonry shall be designed as reinforced for horizontal bending. By using joint reinforcement, the flexural strength of stack bonded walls spanning horizontally can be increased significantly. As a result, the wall for horizontal or two-way bending is designed as if it were reinforced. For all other actions, the wall is designed as unreinforced. Solid and cord units laid in a stack bond pattern, including masonry and veneer walls, shall be reinforced using proper bed joint reinforcement. The reinforcement shall have a minimum area of 0.00035 times the gross vertical cross-section area of the wall. Reinforcement shall be inserted at the following three locations. The first being the first bed joint above or below an unrestrained horizontal edge of the masonry. The second being at least one bed joint within 300 millimeters above and below any horizontal lines of lateral support. And the third being where the reinforcing is vertically spaced at centers smaller than 6 times the thickness of the stack bonded leaf. In general, the reinforcement must have an overall thickness less than 2/3 of the mortar joint, which is approximately 6 millimeters, have at least 15 millimeters of cover to any exposed surface of the mortar joint, be suitably protected to provide the durability class dependent on the environment, and be such that the joints containing the reinforcement do not suffer premature cracking under load, or have an unacceptable reduction in flexural strength. For hollow masonry units, masonry walls must be reinforced or pre-stressed, and designed to resist actions in accordance with Section 8 and 9 of AS3700. The horizontal bending capacity shall be taken as the equation shown, where MD is the design bending moment acting on the cross-section of the member, Phi, which is the capacity reduction factor. This is taken as 0.75 for reinforced masonry. FSY, which is the design yield strength of reinforcement. ASD, which is the proportion of the cross-sectional area of the main tensile reinforcement. D, which is the effective depth of the reinforced masonry member. F-M, which is the characteristic compressive strength of the masonry. B, which is the width of the masonry member of the solid rectangular cross-section. And finally AST, which is the cross-sectional area of the fully anchored longitudinal reinforcement in the tension zone. The design bending moment shall be less than the horizontal bending capacity. Using a standard brick size with M3 mortar and bed reinforcement assumed in every second course, an out-of-plane loading of 2 kN per meter is uniformly distributed onto the wall. A cover of 25 mm is used, and 2 steel bars are used with bar diameter of 4 mm. The design bending moment is calculated to be 0.248 kN. The horizontal bending moment capacity must exceed the design bending moment to meet the wall's robustness requirements. Using a 2.4 meter high and long wall, there are approximately 28 courses. Bed joint reinforcement covers every second course, effectively covering 14 courses. The number of bars in the tension zone is 1, and the area of steel reinforcement is calculated to be 12.6 mm squared. As stated before, the entire section's bed joint reinforcement area must be more than 0.00035 times the gross vertical cross-sectional area. Hence, the wall section meets these checks, as stated below, and therefore is okay to use. A cover of 25 mm is used for the reinforcement. Phi is assumed to be 0.75 for reinforced masonry, and this is found in table 4.4 of AS 3700. The characteristic compressive strength of the unit is assumed to be 15 megapascals. The characteristic compressive strength of the masonry is calculated to be 5.4 megapascals, and this can be found in table 3.1 of AS 3700. The strength of the steel reinforcement is assumed to be 500 megapascals. The effective depth, which is the distance between the center of the reinforcement to the face of the blockwork, is calculated to be 83 millimeters. F0 is the flange outstand and is provided by the reinforcement. It is taken as the minimum of 1.5 times the thickness of the unit, or the length of the unit. Here, 1.5 times the thickness of the unit is used, and the flange outstand is calculated to be 165 millimeters. The effective width of the compressive flange for horizontal bending is 2 times the flange outstand. It is calculated to be 330 millimeters. Here, we are using one steel reinforcement bar, and the diameter of the bar is 4 millimeters. The area of steel reinforcement is calculated, and the maximum allowable area of steel reinforcement is also calculated. As the area of steel reinforcement is less than its maximum, we will be using 12.6 millimeters squared as the area of steel reinforcement. The design bending moment must be less than the horizontal bending moment capacity, which is calculated to be 0.383 kilonewton meters. As the design bending moment of 0.248 kilonewton meters is less than the capacity, this satisfies the criterion, and thus the reinforced wall is okay for the given out-of-plane loading. The association has also curated a stack bonding fact sheet that provides guidance and design requirements of stack bonded walls. It contains a lot of useful information on stack bonded walls, and I highly urge you guys to check it out. If you have any other questions regarding stack bonding, please don't hesitate to contact the association, and we will be more than happy to help you guys out. The association also offers a wide range of free resources available to the public, such as technical manuals, research papers, and case studies. The association also has a technical hotline where we can answer any of your brick or block related inquiries. Should you have any questions about the design and construction of brick or blocks, please feel free to give us a call on the technical hotline. This concludes today's presentation on stack bonding. Thank you for your time, and we hope you enjoyed today's presentation.